All right. Well, thanks everybody for joining us here. I'm going to slowly meander my words a little bit as more and more people pile in. Okay, let's get cracking. So welcome. Thank you all for joining us today for our webinar on the intriguing and hot topic of 3D imaging. We hope everybody's staying safe and healthy in these uniquely turbulent times. Today, we have an alliance of partnered companies presenting for you, including panelists from Photoneo, from North Coast Technical, as well as Matrox Imaging. So we're going to hope to showcase a detailed 3D inspection today using the Photoneo Foxy 3D camera paired with Matrox Imaging's Design Assistant software. So this powerful combination of innovative hardware from Photoneo and versatile software from Matrox Imaging can help to radically improve inspection applications that require a three-dimensional vision component. Today, we're going to show you how to accomplish this, essentially by going over a few example applications and analyzing a 3D depth map in real time using Matrox Design Assistant. As always, following today's presentation, we're going to be conducting a live Q&A session. So feel free to ask any questions you have that you come across during the presentation via the WebEx Q&A function that you see on the right hand of your screen, and we're going to do our best to answer them after the presentation. Please ignore the chat function and use the Q&A function that you see. So to start off, I'm going to introduce our panel for today. Dave Sexton is president of North Coast Technical, which is a team of highly skilled and experienced machine vision experts. They've been servicing OEMs, system integrators, and end users, and they've acted as official representation for Matrox Imaging for nearly 20 years now, and Photoneo now since 2017. Dave is going to be providing us with a brief introduction on North Coast Technical and essentially the array of products and services that they have to offer. Next up, we're going to have Pete Kepf, who handles business development for Photoneo. Pete is the founder and CEO of Fovity Advisors, which is a business development firm that helps machine vision companies grow their North American market presence. He is well recognized in the industry for his many published works, which are authored for trade publications in the US and abroad. Pete is also a proud former US Navy who was in service as a nuclear submarine reactor operator. He holds a degree in marketing from University of Cincinnati, and he holds the CVP Advanced certification, which is actually the highest level of distinction for certified vision professionals globally. Pete's going to provide us with a presentation to compare and contrast traditional 2D with 3D imaging and the many advantages that 3D imaging brings to the table, as well as the features of the new Photoneo flagship camera, the Foxy. Lastly, George Chang is one of the most experienced engineers here at Matrox Imaging. With over 20 years under his belt in machine vision, George started his journey with Matrox as an applications engineer. He now acts as senior sales engineer, managing the US East Coast, as well as Central and South America. George also acts as our team polyglot, speaking fluent English, French, Spanish, Italian, Cantonese, and Portuguese, just to name a few. But George is going to be taking us through a deep dive of Matrox Design Assistant software with its 3D functionality, and he's going to be doing so in English today. And lastly, as your humble moderator, my name is Timothy Labrie Cameron. I serve as lead inside sales representative for the United States here at Matrox Imaging, essentially acting as the first point of contact for inquiries about our products and solutions. So with that, I'm going to hand the microphone over to Dave Sexton from North Coast to get us started this afternoon. Dave.
Thank you, Tim, and thank you everyone for attending. As Tim mentioned, we've been a machine vision distributor for Matrox since 2001 and for Photoneo since 2017. And as you can see on the screen, We have offices spread throughout the US to serve our customers. As a machine vision distributor, we strive to provide everything you need for a vision system, including 2D and 3D cameras, software, imaging computers, and more. We also see a niche for bridging the gap from distributor to systems integrator or in-house vision department. This includes services such as proof of concept testing, custom vision accessories, and software training. What sets us apart is reducing the risk for customers to invest in vision technology. We spend a lot of time supporting integrators and OEMs with proof of concept testing, where they send us their product and we experiment with the best combination of cameras, lens, lighting, and software. The next step to reduce risk is our philosophy of try before you buy. We've made a significant investment with over $1 million in products to loan customers before they buy. This gives an opportunity to test in your own environmental conditions. So if you see anything today that you would like to take for a test drive, please give us a call. We have plenty of Matrox and Photoneo products available for evaluation. And we also have a software engineer on staff trained in both Matrox Design Assistant and the Matrox Imaging Library. Thank you again for attending today. I'm going to pass the baton to Pete for the next phase of our presentation.
So basically, it'll be a review, quick review of the.
Might want to restart there quickly, Pete. I think you were muted for the first portion that you started.
Okay, we're going to go over and do a quick review of 2D vision, and then we're going to discuss the 3D vision. So the comparison and a contrast between 2D and 3D. A quick word about Photoneo and its mission. So the mission of Photoneo is to give robots and intelligence to give vision and intelligence to robots all over the world so they can see and understand it. That's the primary mission. And in order to be able to do that, you have to have a very accurate set of eyes, which can also be used then for inspection applications as well, such as with Matrox Design Assistant. Photoneo has locations throughout the world, concentrated mostly in the US, Europe, and Asia. As you might expect, Photoneo employs over 150 people globally, and 80 of those, actually more now, of those are actually software developers. We've sold over 1,000 scanners worldwide, mostly for vision-guided robot bin picking applications. We have a tech center in Cincinnati, Ohio, actually northern Kentucky, over by the airport. And that's where we provide application evaluations, demonstrations, training, demo units, and that kind of thing. So the Foxy 3D scanners family is comprised of 5 sizes. And I'll show you a graphic later on about why this is important. But basically, I don't know of anyone, any other vendor who has the breadth of the offering from the very small to the very large, and still invest in the same technology. So when you're, you really never know what the application base is going to be when you invest in a technology. And so it really is advantageous when you're taking a look at that to see, well, okay, what's the maximum number of applications that I can address with that. So why would we use 3D? Well, the simple answer is that it provides solutions for inspection and guidance that would be difficult or even impossible to do with 2D vision. So uh, your typical 2D vision system consists of a camera, some sort of way to collect the light, a lens to focus the light onto the camera sensor, and then different sorts of lighting. So you can have hyperspectral lighting, for example, IR, a number of different frequencies of light, different shapes and sizes. If you've worked with 2D vision, you know what I'm talking about there. You start with a 2D pixel camera sensor. And then to that, you add a lens, which focuses that light over that pixel matrix. And the pixel matrix then now, when we see what the intensity of the light is at each particular pixel, we can begin to get some information about what's in that image or what's in the scene that we're looking at. We can get grayscale information, we can detect edges and patterns, and we know size and shape because we know what the horizontal and vertical addresses are for each one of those pixels and the corresponding grayscale. So the data that's returned is X and Y position and intensity from 0 to 255. If 0 being black and 255 being white. If it's a color camera, what they'll do is they'll put a filter over each one of the pixel, a different color over each one of the pixels, and then there's software that decodes the various grayscale values for what the corresponding colors would be. To calibrate then for size, what we do is we put a known grid, something known dimension in the field of view of the camera. Typically it's a dot grid, doesn't have to be. And then we know what the distance is between the dots. And so because we know what the distance is between the dots, then we can translate from pixel space to world space. This can also compensate for lens aberrations. If you look at the dot grid, for example, on the left-hand side there, this lens is returning some aberrations, particularly on the periphery. But if we know what the distance is, the software can compensate for that. And as long as nothing changes, we're good. As long as the focal length, the working distance, field of view, the lens doesn't change, then we will have repeatable measurements. 3D structured light scanners are one type of scanner. They approach the problem a little bit different way. What you'll have is a laser projector on one end of the column, and you'll have a sensor, which actually is no different from a 2D sensor. It's just a 2D sensor, industrial camera sensor, and a GPU on board. And by projecting a series of patterns, you get some light displacement. And you'll see by triangulation, then you'll be able to see what the patterns are and what the depth is. So again, you start with a 3D, with a 2D, same sensor, same type of sensor that you have with 2D. Same kind of a lens, still focusing that light intensity information onto the pixel matrix. But this time we're projecting a number of different patterns. And depending on what the part geometry is, those patterns, even though we know what the pattern is, but if we know that it's supposed to be a straight line and it isn't, then we know that there's some positional displacement there. So for example, if you look at your target with the ball here, those lines are supposed to be straight. The software just as we calibrated with the dot grid, software thinks that they're supposed to be straight, but it says, oh, well, they're really not. So what's the geometric relationship based on the apparent positional displacement of the patterns? If you project a number of patterns or a sufficient number of patterns over an object, you can really get some detailed information on the geometry of that of that object. So in comparison to a 2D sensor, what you get with a 3D vision, the data, is that you'll get the intensity from 0 to 255, same. You get X, Y, and Z location. So in addition to the horizontal and vertical, you get a depth location. And the difference then, so there's a term, the voxel, which is a volume pixel as opposed to a pixel used in 2D. So in 3D world, they're called voxels, and that's the location within a point cloud. And that can also be calibrated into world units. The difference is, though, that the calibration relationship, the relationship between the light source and the lens or the sensor always remains the same. So the 3D scanner is internally calibrated, and it will remain that way. And it's calibrated for a certain volume, certain focal length, and if you look at the pattern to the right, the pattern is a little bit different because it actually has data in it. So in order to compensate for parallax, remember what we saw in the 2D dot grid, there's a certain amount of parallax there and distortion. So that can be compensated for if you have a matrix or calibration matrix with data on board. So what you'll see here is in the yellow is the laser, the purple is the field of view of the camera, and because they're all fixed, we know exactly what the positional relationship is in voxel space or in the point cloud for the entire volume of the working distance. So again, working with 2D, we hit pixels, we can pick things out because of the difference in pixels. Working in 3D, we're working in voxels, and similar concept except another dimension. 2D vision, you have focal length, field of view, and working distance. And that's dependent upon the angle of the lens, the focal length of the lens and the angle. In 3D vision, you have a work envelope. And the work envelope is obviously in 3 dimensions. It also has a focal length. There's a sweet spot, what they call the sweet spot or the focal distance. But it's important to know that within the blue working distance, the blue work envelope, when it's calibrated, all of the calibration is valid within that blue. Now, that doesn't necessarily mean that that's the limit. If you want to work out of calibration, you certainly can do so. For inspection, for example, if you don't really care, if you're doing say a 2D inspection as a part of a 3D and you're out a little bit, that's fine. You can work with that. And again, the reason is that just as in 2D world, you've got a certain depth of field, a little bit of flexibility there that you can work with. You have the same thing in 3D world. Again, the optics are the same. We're just working with a different structured light. So the Foxy 3D scanner product family, then, if you look at the specifications to the left, the purple, the little XS, the optimal working distance there is 181 millimeters or about 7 inches, with a field of view of 4.45, 3.27, so about 4.5, 3 inches, and a resolution, which we can't, it's tighter than 2 decimal places. It's actually 0.06 millimeters of a resolution. Now, resolution is different in 3D land than it is in 2D land. Resolution in 3D land is the distance from one voxel to another. Just as in 2D land, it's a distance from one pixel to another. The calibration accuracy is that's kind of a misnomer. The calibration accuracy is actually a repeatability measurement. It's how from one scan to the next, what's the repeatability of the image that I get. So you can see we can get some really tight tolerance measurements with the XS because the field of view is small. But even with the XL, if we go to the other extreme, the XL, that has a 91-inch optimal working distance with 76 and 59 respectively for Y and X, and yet it still has 40 thousandths of an inch of resolution across that working distance. So we have a working distance of 8 feet thereabouts, and we can still go down to 40 thousandths in resolution. And also, just as in 2D land, where you combine pixels to give you a tighter resolution than pixel by pixel, the voxel resolution works the same, because you can statistically determine based on the intensity of the voxels and their location geometric attributes. So what kind of applications would we see with 2D versus 3D? Well, in 2D, if you're looking at the surface, that's where 2D really shines. It's also, no question, you can get higher resolution with the megapixel cameras and the various high performance lenses. You can certainly get a higher resolution for metrology. You wouldn't do metrology with 3D, for example. If you're looking at image features such as barcodes, labels, if you want to do color, so 3D doesn't really do color the way you can do with 2D. And if you're moving fast, well, it takes time to handle all of the data on a 3D system. So if you have a high-speed application, chances are you're not going to do it with a 3D scanner. But if you're interested in a profile and you need shape information, location information in 3D space, such as some of those applications there, then absolutely 3D is the way to go. And you can get, and George will show you here in a few moments, that you can do inspections in Matrox Design Assistant in 3D that are impossible to do in 2D. So for example, he's going to talk about the cookie and the depth of the cookie, and you can do coplanarity in 3D, which is impossible almost to do with 2D. You can look at other surface, and of course, for vision guidance, 3D is absolutely a must nowadays. So we can't wait to see what George is going to show us with Matrox Design Assistant, and I'll turn this over to George.
All right, here we go. Perfect. Thank you very much. And thank you, Pete, for that primer to 2D and 3D. And thanks everyone for tuning in into this webinar. In this part of the presentation, we will go over some of the software aspects of 3D inspections. But before we do that, I would like to introduce our company, Matrox. We're a Canadian company with over 45 years of experience in the electronics industry. We're headquartered here in Montreal, Canada, where we house our own sales, marketing, engineering, and we have our own manufacturing facilities. But we're also a global company with offices in Europe and Asia, and with representatives in over 20 different countries, with the North Coast being one of those key partners. Maybe a little known fact about Matrox, we actually hold over 120 US patents related to machine vision. And we're actually very involved in specifying industry standards, such as GigiVision. So you can say Matrox is quite in the forefront of technology and innovation. In fact, companies around the world use Matrox to build their inspection systems in different type of industries, being electronics, automotive, semiconductor, packaging, and medical imaging. The software we wanted to talk to you about today is called Design Assistant, or DA for short. It is a flowchart-based development environment. You can actually configure capture, inspection, PLC communication, robot communication, and controls. And we actually have anything from 2D, 3D, and even deep learning tools. You can also configure data storage, archiving for historical and trends. You can also configure a customized HMI or display. So all this is integrated within this Design Assistant environment. And once you're done with your application, you can actually deploy it to either our Iris GTR smart camera, which is a standalone smart camera system. You can also choose to deploy it to our Foresight EV6 industrial computer, IPC, with Gigi vision cameras. Or you can also try to deploy it into your own PC, your own industrial PC. In this case, you're basically reusing the same software, which is Design Assistant, for multiple platforms. Now, when it comes to the Photoneo camera, it's interesting because DA integrates direct capture from the Photoneo camera into its environment. That is, you can actually capture a 3D image, pretty much like if you were to use a Gigi camera and grab it into our Foresight EV6, for example, for image processing. It is that simple. So what we have for you today are actually 4 use cases for 3D, and we will go over each one of those in our Design Assistant environment. So the first use case, again, we're trying to figure out the volume of a cookie and making sure that it's not cracked. I have a few images of a cookie over here, a few cookies. Some of them are half broken, some of them are intact. And what you're seeing over here is the Design Assistant interface. Basically, again, you create an application by putting together a flowchart. You have a live display of each of these tools. On the right, you have a multi-purpose panel here where we actually show images or any variable in your application. Here on the bottom left, we have a configuration pane. We can actually configure each of these tools. Each of these little rectangles represents a tool. We call it step, and each of those steps has its own configuration pane. And here on the left is probably the best part of Design Assistant, that you can actually step through your project and see individual results of each of these individual steps. So here, for example, again, this is an already made application. And the whole idea, again, it's using 2D tools on a 3D image. And we'll show you how we can actually do that. To this, I'm going to run the flowchart one loop. And we're going to see how we achieve this project. So let's start here on the top. We have the camera step. The camera step enables me to take a picture from a Photoneo camera, or in this case, I'm able to load a 3D picture that was previously captured with Photoneo. I can choose to look at the grayscale image, or I can also take a look at the point cloud, or in this case, sorry, the depth map. The depth map over here, you'll notice that the values are actually calibrated. If you'll see over here on the bottom right, I'm going to try to use this annotation tool on this side. You will notice that when I hover my mouse around the area, I'm going to see millimeters instead of pixels. I actually also chose to color code the different heights, with blue being closer to the conveyor belt and red being the highest most point. In this case, we show here that we're about 10 millimeters in height for this cookie. And that's pretty much it. This is what we have from the camera step. Next step, to calculate the volume, we have a blob analysis tool. And blob analysis can return the sum of the heights, which at the end will become the volume. So it's actually telling us that the volume is about 27,000 millimeters cube. In this case, we can also put a verification or a check to make sure that this value is within our pass-fail tolerances. Next step, we have an intensity checker to check if the cookie is actually broken. If I have a very even contrast, for example, that means that the cookie is intact. But if I start showing a contrast that is higher than my tolerance over here, that could signify that I'm seeing part of the background, which could signify that the cookie is actually broken. The final final step in my flowchart is the status step. And the status step is basically a status collector. So it was actually going to check the pass-fail for my blob, in this case the volume, if it's within my tolerances. It can also check the pass-fail of my intensity checker to make sure that there's no broken cookies. And it will give me an overall score as an overall pass-fail. So we're going to go ahead and step through and see some of the values that we have with the different samples of cookies. So this one is saying that it's a pass because volume and intensity check and pass. This one is a pass as well. This one, it's a fail because there's contrast that goes beyond my tolerance, as well as volume is not complete. And so we have another one that is broken, and so on and so forth. So again, Design Assistant is able to build an application fairly easily to inspect volume as well as cracked in the cookie. And obviously this could be useful in food industry, verifying content, verifying volume, and portioning, for example. And again, we're using 2D tools on a 3D depth map. Once we're satisfied with the logic, we can go ahead and build our operator view, which is a customized HMI. You can actually add buttons, pass-fail, results, and values. And once you're satisfied with the look and feel, you can choose to deploy the project with this button. And what you will see is actually the project running on a web page. It's a web page-based HMI, and this is the application. You are able to, again, indicate pass-fail lights and showcase some of the results. You can go in triggered mode, and show fail or pass, or run in continuous mode, right? So this would be something more along the lines of an actual inline inspection. So once again, the concept is using 2D tools on our 3D depth map. And as you can see, you're able to build a project by building a flowchart. Very easy to use, very easy to set up. So this is the first use case we have for you. The second one, it's actually one that involves verifying an assembly. Here we have an assembly of connectors. And the task is to find a reference point or a fixture point and add 2 checks for intensities or heights and making sure that they're at this at the same height level. So we're going to see some of the sample images that we got. And just like in the other example, let me run one loop of this project. And I'm able to see what we're doing. So here we have the camera step again. This enables me to load a 3D depth map. Then I have a pattern matching tool to actually locate a fixture point. In this case, it's the top of the component. I then go ahead and specify one ROI or one sampling region where I want to check the height. And it's actually telling me that the height is a specific value that I can see over here. I use the same reference point to indicate a second region of interest, more in the connector. So I'm going to see that on this intensity checker. And in this case, I'm able to actually put a condition and verify that this 2 should be, or the difference between these 2 should be less than 1 millimeter, for example, to make sure that this is a pass. After that, I can add a measurement tool to actually measure the width. And this is a 2D measurement, the width and the height of the adapter, and as well to put in my pass-fail conditions, if it's in range or greater than or smaller than. And at the end, I have the status step, which is, again, a collection of all the overall pass-fails. And we can actually see that in this particular case, for this connector, we have a fail in the clip height because this region and this region are not at the same level. That's our pass and fail condition. It should be less than 1, and it's actually about 4 millimeters. But in width and height on the 2D measurement, it's a pass because they're within my ranges. I can cycle through another couple of samples until I find one that actually passes. Here again, the value of this intensity checker and this intensity checker are within my tolerances, as well as the X and Y. So again, another very simple to put together 3D application using Design Assistant and using our 2D tools on the depth map. This type of approach, again, finding a fixture point and then putting multiple regions for height inspection is very useful in, again, in different type of kitting applications where you want to detect presence, absence based on height, in case that the 2D image doesn't give me the information. All sorts of assembly verification as well. Again, we can inspect heights in those cases. The next use case we got for you, it's a very simple pick and place application. Again, we have a few electrical connectors that are bundled in a pile. And the idea here is to find which one is on top. For that, we can actually then send the coordinates of our location finder or pattern matching or model finder tool to an end effector that could be a magnetic one or a suction cup to go to those coordinates. So we'll see how we actually achieve that. In here, first of all, I use a model finder to find potential candidates for sampling my height, my different heights, and actually have my model defined over here, the electrical connector. And once I find all the 3 potential candidates, I do a loop, try to cycle through all these candidates and try to find which one is on top or the topmost. And then for that, I actually keep the index of the topmost and pass on the index and the location to my pick and place robot. So here, for example, the intensity checker is telling me that for the first one, it's calculated a specific height and it's this value. Then I go ahead and cycle through the second candidate and the third one. And actually I keep the topmost one index, for which I then pass on, again, the location or the XY location. In this case, I'm able to see that the model finder returns the position, XY coordinates, to my end effector. And at the end, I go ahead and do this for all my parts. I'm able to do this once that's picked up. I'm gonna go ahead and try to sample the next scene or field of view, the next scene. And again, this is a typical pick and place application where we are able to find the topmost item in the pile. And the last use case we got for you today, this one is a very interesting one. The challenge here is to determine if this metal plate that has a drill hole in it has a plug that is inserted in there. So not just actually presence absent, but we need to find if the plug is inserted flush to the surface, so parallel to the surface. This application comes in very commonly in automotive, for example, if during the paint process, if there's drill holes, you need to drain the liquid or paint. At the end, you need to put in plugs to make sure that those drill holes are properly plugged in. Again, it's most of the time it's a human process, and we need to verify that the plug is properly plugged in and flush to the surface. So we'll see how we're able to achieve this. I'm gonna cycle through some images, and you'll see that they're placed in different parts of our field of view. And again, these were taken with a Photoneo camera. And some of these images have a plug, some of them don't. And you'll see that the plate is placed at different angles, right? Not just in 2D, but in 3D. So we're gonna go ahead and use our flow chart. We're gonna run one loop of this flow chart. We're gonna run it through the end. And we're gonna diagnose what was done actually. So we look at here, in this specific case with this image, our camera step loads or captures a 3D image. We have a tool called Ellipse Finder that will actually find the location of the plug. So in this case, or in the drill hole, ellipse finder is a very powerful tool. Gives me a position. Then we have a new tool in Design Assistant 7 or EAX7, which is the plane alignment. So this tool, what it does, it will actually align all our measurement tools to a specific plane. And in this case, we made it to align to the metal plate. So in this case, we align it to this metal plate, plane align tool. We then use a tool called profile extractor, extract a profile. So what we do over here is once we have a fixturing point, we define a line based on this fixture point, which will go across the plug, in which it will actually give me, again, the profile of this plug. And at the end, I apply a metrology tool to verify the different heights of my plug. So again, I actually added 5 different measurement boxes. The 2 on the side are just measure the plate. Again, this profile, this metrology I'm seeing is based on this line profile that I have defined over here. And the other 3 measurement boxes are actually verifying the different heights of the component of this plug. Here I'm seeing the left, let's call it left wing of the plug. This is the center of the plug, and this is the right wing of the plug. You see, it's one of those type of plugs that have 2 concentric rings. So in this case, it's telling me that, hey, the left side of my plug is higher than my right side. And we're actually able to see it in maybe in our camera step. So we actually can go in and zoom in. And yeah, effectively, it looks like, you know, this side is a little bit higher than the other side. So again, this is the power of Design Assistant. We're able to verify not just presence, absence, we're able to verify in here, but also if a coplanarity, if a object is to a specific standard or a specific plane with another one. And here, like you all know, the status step is it's basically a collection of all the pass fails of my individual steps, and I'm able to see here that for plane alignment, it's a pass, but for metrology, it's saying that the left side of the plug is actually higher than the other side of the plug. So that's one of the results of my inspection. So we're gonna cycle through a couple of them just to see how this actually performs. Here, for example, it's telling me that the plug is not present because the metrology is telling me that in the middle, my measurement is not even there, right? So it's outside of my spec. For the next part, I'm able to see that the plug is there and it's actually flush against the metal plate, right? So we see that, and we're able to see run the same project, although the plate it's placed at different angles. So this is very interesting for all sorts of applications that they have, you know, different drill holes at different angles, and we could actually extrapolate this for multiple drill holes. Again, pretty much like the same process that we had with the pick and place application, where we loop through all occurrences, right? We could actually do the same for our drill hole in case there are multiple drill holes and multiple plugs. So this concludes our 4 use cases for 3D inspection. And again, the message is we're using some of our 2D tools on a 3D depth map into a flowchart, which is easy to use, easy to put together, and you're able to build applications in 3D. So going back to our presentation, just to wrap it up, you can tackle 3D inspections today. Design Assistant and Photoneo have made it very simple to capture. Again, the Photoneo camera becomes almost like a point and click camera, but you actually get 3D information. We get very high performing 2D tools in Design Assistant that can be applied to this 3D depth map. We get circle finder, model finder to locate and fixture. We got blob analysis, intensity checker to verify volume and height information, and a lot more tools in the Design Assistant interface. And new in DAX7, we get new tools like plane alignment and metrology in 3D, which provides even more capability for 3D inspection. And all of this without the need of traditional programming. Back long gone are the days where you have to program C# just to program a graph. And I'll conclude my part of the presentation with maybe sharing a pro tip. And I think this is very applicable to these days of working from home. You could actually use to capture images from Photoneo and store those 3D images for offline development. A lot of times you may not be able to be close to the setup, so you can actually go ahead and take a picture, all the 3D images that you need, and work offline, pretty much like I have shown you in this 4 use cases. Well, with that, I finish my part of the presentation. I'll pass it on to Tim to conduct our Q&A session.
Thank you, George. Thank you very much. Thanks, Dave, Pete, and George for taking the time to present with such clarity. Very, very cool technology being displayed here. I especially like that simple web-based operator view. I thought that was really, really cool to see in action. So yeah, with that, we're going to go ahead and conclude with a brief Q&A period for our attendees. As I mentioned previously, if you have any questions for our panelists, feel free to write them within the Q&A function that you see on the right hand of your screen, and we're going to try and get to them. I see we already have actually some questions loaded up. We'll also be glad to address any more detailed questions that you might have offline. So feel free to reach out and email Dave, Pete, George, or myself at the emails that you see on your screen now. And we'll do our best to get back with you after the webinar is concluded to help answer them. So with that, we're going to move forward to the Q&A. I'm going to read out the incoming questions, and one of our panelists are going to jump in to respond based on the nature of the question. So the first thing that came in here was actually through the chat line, and that is, will the slide deck be shared with us? And I'd imagine that is a question regarding to the entirety of the presentation.
Yes, certainly. We can make this information available. We can even provide a copy. Sorry about that. A copy of the recording for you. Just feel free to contact any of us, and we'll gladly forward you this information.
Right. Okay. Are there loaners available for us to evaluate the technology?
Great question, Tim. Yes, as we started off in the beginning slides, North Coast has plenty of demo units available for evaluation. So either reach out to myself, or if you know one of my guys, please reach out to them.
I figured that was a Dave-related question. Let's see here. Can DA load a PLY file from the disk and use it? George?
Yes. Yes, certainly Design Assistant can load a PLY file. In fact, I have a quick, oh, here it is. I have a quick project showing that you can actually load the PLY. And from that, use a image projection to actually project it into a depth map. And again, pretty much like this, the use cases we show you, be able to apply 2D tools to our 3D PLY or depth map. So the answer is yes.
Very cool. I guess good chance that you had that up on your screen. Okay, this sounds like a Photoneo question. Yeah, can I use a 3D scanner like Photoneo and a 2D camera on the same system? Good question, I think.
So the answer is it depends. That's really a software thing, because the output of the scanner is the scanner is just a 3D point cloud camera. So whatever the input software is, if it will accommodate two different signals, if you've got a frame grabber, for example, with two channels, chances are you can do it. So the answer is maybe.
Yeah, I'll just jump in on the Matrox Design Assistant side. Certainly, you can create a flowchart with multiple camera steps, and each camera step can represent either a Photoneo camera or a Gigi or USB 3 vision camera. And all those can actually be plugged in into our Foresight EV6 industrial PC, which counts with 4 PoE ports. So you can actually directly plug in up to 4 Gigi PoE cameras in addition to the Photoneo camera.
Okay, I think that answers that question. And actually related to that, does Photoneo need drivers to be installed in the PC with Design Assistant?
Photoneo does not need drivers. All of the software that's required is loaded in the configuration file. So just like any camera, you'd have a configuration file. We didn't talk about that, but you can adjust the various parameters, such as the scan time and intensity, and there are just tons of different adjustments that you can make to the scanner. And that software, that configuration software, has everything you need. You just plug it in and it works.
Let me just jump in, Tim, also from the Design Assistant perspective, we do need the Photoneo software to be installed on the same PC or platform that we're going to run our application. So yeah, we need the Photoneo software installed alongside with Design Assistant for applications.
Yeah. Yep.
Okay, here's an interesting one. I believe that Pete mentioned that you wouldn't do metrology with 3D applications, yet Matrox has a metrology tool within Design Assistant. Can you speak to the challenges of 3D vision and metrology tools such as non-contact gauging?
So do you want to take that, George, or do you want me to take that?
Yeah, certainly. I'll just quickly jump in. So we were doing some 2D metrology on the Photoneo image. Keep in mind that the image that's presented by Photoneo in terms of 2D has some sort of or specific type of resolution. So our 2D tools applied to the image provided by Photoneo, based on the image itself, may not have the same resolution as, let's say, taken by a 2D camera, right? So we could apply 2D tools to both the 2D and a 2D Gigi camera and the 2D image from the Photoneo camera. But my feel is that probably with the 2D Gigi camera, we may have better or sharper resolutions. But it's all dependent on the application. If the image provided by the Photoneo camera in terms of 2D has or meets the metrology requirements, then it could be used by all means. So it's application dependent. But Pete, maybe you have anything else to add there.
No, I was just speaking in general that, if you're looking at metrology in general, chances are you've got, with a 2D camera, you're going to have sensors with much higher resolution than you're going to get with the, with the point cloud. That was the point I was trying to make.
Yeah.
Okay, so maybe
Let me do a quick jump in if you don't mind.
Sure.
Yeah, I mean, metrology is kind of a broad tool, and I would encourage customers to reach out to your North Coast technical representative to discuss your application. It certainly can do measurements, as George mentioned, and it is application dependent, but please reach out. We'd like to learn more.
Yeah, you took the words right out of my mouth, Dave. That sounds like a question to follow up with online and get into the nitty-gritty of the application. Okay, and actually that kind of segues a little bit into the question here. I think you kind of touched on the answer to it, George. but how is resolution calculated when I'm using a depth map?
Yes. Again, this is probably project specific. We can go over that in a separate conversation. So yeah, certainly. But just quickly, in terms of 3D resolution, well, Photoneo has its spec where you have the X, Y, and Z resolutions to the millimeters of precision. So that is taken into account when you calculate an application, and you just want to know if the result from your capture will be within the tolerances that you need to measure. So it's all by the spec. Photoneo has a spec for resolution, and you just need to figure that out with your application. But certainly, again, please reach out to me, and we can guide you through that.
Okay, I have a couple of other questions here. I don't think we're going to be able to get to all of them this afternoon, but again, we are making note of them, and we will follow up with the people asking the questions for some more detailed answers here. But just quickly, in the software, so in DA, can we perform picking application and inspection at the same time?
Yes, we can. So the example we saw over here with the pick and place, we determined the height of the topmost part, but certainly we can apply all sorts of inspection to that picture, or maybe present it to a second stage and do inspection in there. DA is a very powerful tool. You're able to do many things from, again, 3D, 2D inspection, 3D inspection, and even apply deep learning tools on the image.
Fantastic. So short answer to that is yeah, we can.
Yes, we can.
Okay, and here's a question I like to see. Who do I contact for an on-site demonstration? I'm pretty sure I know who would handle demos for us.
Absolutely, Tim. Thank you for the great question.
Why is it North Coast?
Absolutely. Please reach out to the email address on the screen.
Okay, all right. So let's go ahead and wrap that up then. We do have, like I said, some other questions we weren't able to get to, but don't worry, we will get back to you privately here with further information. And again, if you do have any questions that kind of come to fruition after the presentation today, feel free to email any of the four of us here, and we'll do our best to help. Okay. So thanks again for joining us. Stay safe, and look for our upcoming webinars, as we're going to be putting on more and more of these things in the future.
Thank you, everyone.